Hello everybody, today we're gonna be looking at AMMs on StarkNet. I am Carlos and I'm gonna be explaining these following outline for the rest of the session. So we're gonna be talking about introduction to AMMs, and then we're gonna be looking at Uniswap v2. We're gonna go through the architecture, some core concepts like token ratios, price, swapping, adding, removing, liquidity, and finally, we're gonna take a brief overview over flash loans. So at the end of the session, we will be also coding a Cairo version of Uniswap v2 pair contract. And then let's get started. So an introduction to AMMs. So AMM, the core idea of AMMs, it stands for automated market makers. These are basically contracts that hold two tokens, as you can see here in the picture. So the term automated refers to the automation of the pool rebalancing. So this is done through the code itself. And the logic is very simple. The product of the balances, as you can see here, A prime times B prime has to be greater or equal than K. So this is something called as the constant product formula. And what it says is like basically the balances of token A and token B in the contract have to be always at the very least constant. And when I say the very least, it means that this product can increase due to some incurred fee that most of the pools have. And well, actually in the real life scenario, most of the pools will have a certain fee. There's a fixed fee of 0.3% on Uniswap v2 pair contract. And something that I want to address here is also that the main actors in this system are liquidity providers, because they are the ones who provide tokens, balances to these systems. And then on the other side of the pool, we have the traders. So the traders are the ones who will be paying fees for each trade, and they will be making the price fluctuate according to time. And then something to mention here is that, for example, the standard of ERC 4626 allows for just one token, but this is something similar in which you will be holding a share of both tokens, token A and token B. So it's kind of like a vault pool that holds two tokens. Then I'm gonna explain why we use AMMs, and then why we shouldn't use AMMs. So why AMMs? Because the pricing is automated. Basically, it means that at any time the price of token A will be equal to the reserves of B over the reserves of A. There is no need to use a mechanism like order books where users place a bid on a token price and waits for an ask price to show up, or a matching order. The price there here in the pool is the one you see, and is the one you can trade as long as there are enough assets on the pool. The next thing is that AMMs are very efficient compared to order books. The maintenance, development, and the gas is also very efficient. And the rules are very simple. You get a price, you trade upon the price, and then the token price will be different after each trade. And then the final advantage that AMMs have are that they can serve as oracles too. But I'm not going to stress here because probably there are some intricacies and some points to consider when building oracles on AMMs. Now let's talk about the disadvantages of AMMs. Okay, so because of the constant price fluctuation, we assume that every single swap will impact the price. Of course, in larger pools, small swaps don't mean much, but in very small pools, the bigger swaps will definitely change the price of the tokens by quite a lot. So this is just something to consider. I would say it's a bit more risky if those are very small pools. And then the second thing that I want to mention is the sandwich attacks. I'm going to explain here through one image that I wrote. So sandwich attacks, as it says, basically you as a user, you place an order, and there will be an attacker that's going to place one order before you and one order after your order, such that they profit. In this example, we have a USDC ETH pool. We can assume, for example, that, okay, if you place an order, like you're swapping USDC for ETH, it means that after the trade, there will be less ETH in the pool because you're getting ETH. and more USDC. So the price of ETH will increase because there is less amount of ETH on the pool. Okay, so your trade will increase the price of ETH. Now, if someone replicates the anatomy of your trade, they come in before you and they will increase the price of ETH before you actually trade it. So you will be getting ETH at a higher price. So the expected amount of ETH that you're getting is going to be less than the actual amount you get, right? So the attacker at the end, because the attacker bought ETH at a certain price, then he increases the price, and then you buy the ETH and you increase the price again, the attacker is going to end up profiting from that trade. And that is what it's called as sandwich attacks. And these AMM systems allow these type of attacks, and these are very common in blockchain. Now, at the very end, I want to say that there are limited features as well for AMMs. So basically, because the system is very simple, you cannot build hooks or things on top of them or extend them because they are just kept to the minimal. Okay, now let's take a look at Uniswap v2 architecture. So we have two parts, right? The Uniswap v2 architecture, one part is the core. So the core is basically the ones that I put in the circle, and there is the periphery. Periphery contracts, you can imagine them as some helper contracts that will allow you to interact with the core contracts. That's it. So the core contracts are two, the pair factory contract and the pair contract. And the pair contract has the main logic of what Uniswap v2 is, and actually it's what the white paper talks about the most. Pair factory contracts, as it says its name, it's going to deploy different types of pairs given a couple of token addresses. And then the periphery contract here, the router, we call it the Uniswap router, is just a helper contract that will help users interact with them such that their trades or whatever they're trying to do with a pair contract is safer than the user interacting directly with these pair contracts, because these are all contracts. The users can interact with any of them. However, the pair contracts has some checks, some things to take a glance before you actually perform some operations on, and that is handled by the router contract. We're gonna take a look later at some sample code. All right, now that we finished the architecture of Uniswap, we can take a look at how token pricing works on Uniswap. And I'm gonna share my screen and show how this mechanism works. It's very simple. And actually most of the the AMM concepts are all showcased in Uniswap contracts, because Uniswap is one of the main actors out there that build AMMs, one of the first ones to build AMMs. So let's just start with token prices. The main formula that Uniswap uses is basically the A times B has to be greater or equal to K. And that is not actually, it has to be like A times B equal K, but when we say it's greater than or equal to K, it means the pool will be incurring some fees along the way, and this is allowed. And something to point out is that Uniswap is not going to put a penalty on you or penalize you for sending more tokens than you should to the pool. So that's why we mentioned before that we use something called as the router contracts as well. This relationship basically shows the inverse relationship between two tokens. It's doing the market demand and supply from one and the other. And the way it works, I'm gonna go with a graph. So if we plot something like this, and we've got, let's say 200 here, this is ETH. This is the price of ETH, or the amount of tokens of ETH. And here we've got, let's say 1000 USDC. We can draw the product in this part, and then we can have some curve on this side. So we can think of this part as the minimum of the amount of the product that it can reach. So this thing that I'm gonna show here is what the product has to be always. So it has to be at least on this line that I show. And then something to mention also is the fee of Uniswap. It's fixed to 0.3%. And that is something that is already hard-coded onto the contract of pairs. Then something to point out is that inside the code, Uniswap basically will check that the K before the swap happens, it's less than or equal to the K after the trade happens. So you can think of that the X before times the Y before has to be less than or equal to the X after times the Y after. Now, if you want to find, for example, the correct amount in of tokens, you cannot directly just send the proportion of a token compared to the other inside the pool, because you have to also consider the fees on the token. And sometimes people, if they want to use these contracts like directly, they will be sending some ETH or some USDC. If we're talking about a pool here, as I mentioned, a ETH USDC pool, so people will be sending some ETH and USDC, but they will not be able to calculate precisely. So that's why, again, I stressed on these routers are for. Routers are made for like basically taking away all the hassle for users to trade on these token pairs. Okay, now that we look at pricing and how these A times B greater than or equal to K, and the location it's situated inside the graph of a USDC ETH, as you can see on the graph here. Now we're gonna be looking at how the swap works, and we're gonna go to the source code of Uniswap. This is the main Uniswap v2 pair contract, and let's search for the swap function. So the swap function, it's going to be very simple. Let's focus on this section first here. This is something very important. So as you can see, the swap receives two inputs, and these inputs represent how much of each of the tokens do you want. So that the amount 0 means how much of token 0 do you want and how much of token 1 do you want, right? And the address 2, of course, is who is the receiver of this. And bytes call data, it's extra call data is like some information that is going to be executed on the receiving contract, which is represented by the 2. So if we look at these lines here, we will see first is going to check, okay, if you have amount of token 0 is greater than 0 and the amount 1 is greater than 0, I'm going to transfer them to you. But there's no checks here before that. I'm not doing anything else. There's no requirements on the K, for example. So the K requirement is at the very end of the function. So what this allows is for something that is very important when Uniswap v2, that is flash loans or flash swaps, as they call it on their white paper. Flash swaps are performed through this call in this line. So what it does is, like in a summary here, it's transferring the tokens before you actually check for the K. This K check on the side represents the check that I just mentioned before. So it's going to check that this product lies down at least on this line or this area here. So if it goes below, like in this graph, goes below, it's going to fail. And this is the way Uniswap makes sure that the amount of tokens you are sending with your swap, it's actually correct. So if let's say you want to swap some tokens, you want to get some token amount 1 out, you want to get, for example, some ETH, you will have to first send some USDC into this contract and then call the function swap, and then you will be getting, of course, your ETH, because this is what you want. And then the contract is going to call a function named update, which is going to overwrite the current reserves that are being kept tracked inside the contract. So this is very important. Again, you get the tokens even before the K is checked, and this allows for flash loans that I'm going to explain in a while. Okay, now let's take a look at how Uniswap v2 adds and removes liquidity. So in the source code, they don't have any add and remove liquidity functions, but the two functions that represent both these are going to be the mint and the burn. So let's take a look first at the mint, and let's just keep this minimum liquidity section here. So let's suppose that the pool has already some tokens, right? So the total supply is not 0. Let's suppose that. What it's going to do is going to get the reserves first of tokens. So it's going to tell me how many tokens do we have recorded on the contract until now. And then it's going to check for the balances. And after that, it's going to subtract the balances, which are like the real time token balances. And it's going to subtract with the recorded token balances. to get the amounts. Once the amounts are already there recorded on the function, it's going to mint the fee. I'm gonna skip this section here because this is minting fee, which sometimes is on and sometimes it's off. So let's just skip this line. And let's suppose the total supply, which is how many shares have been minted until now, which means whether the pool has liquidity or not. It's not zero, so this is not zero. Let's move into the next one. So what this is going to be doing, it's going to calculate how much liquidity these amounts represent on the pool. So this is of course done through a multiplication and a division of both. So you can see it's going to get the minimum of both the amount 0, the first token, and the second token, the proportions against the total supply. Then requires that the liquidity is greater than 0, otherwise it reverts. And then it means the tokens to the user that we specify in the parameter 2. At the end, it's going to update the balances of both of the recorded balances, the tokens, the ones that we got at the very first line. Then in the FSON, it's going to update the K last that basically will keep track of the constant product formula. Now let's take a look at this section here. The total supply equals 0. So the total supply equals 0 means that basically there's no one who has deposited here, and no one has met the minimum liquidity requirement. And the minimum liquidity requirement is a requirement that Uniswap set on their white paper to avoid for certain attacks. And also, this is very important here, the square root of the amount, the first amount, and this multiplied with the second amount. This is the geometric mean formula for both amounts, and this is explained on their white paper, as we can take a look here. It says that Uniswap means shares equal to the geometric mean of the amounts deposited. So this formula ensures that at any time the pool share is basically independent of the ratio of which liquidity was initially deposited. All right, so this formula ensures that the liquidity pool share will never be worth less than the geometric mean of the reserves in that pool. But as we saw before, these can keep increasing, and because it accumulates trading fees through donations to the pool. So this is the reason that Uniswap used to implement the geometric mean formula on their MT pool. Okay, now so let's take a look at how Uniswap removes liquidity. So we first took a look at the mint function. Now let's take a look at the burn function. The mint function will take the two amounts that were transferred to the pool and then calculate the portion of them, the minimum, and then transfer those pool tokens to the user. Now the burn is going to do the opposite. It's going to calculate how many of these pool tokens were sent to the contract. As we can see here on line 140, we see that there is a balance of address these, which is telling me that this function is calculating how many pool tokens are available and owned by this contract, the pair contract. And then it's also going to get the balances of both tokens that are in this contract. This function here, the reserves, or as well the track balances, as we mentioned before. I'm gonna skip this mint fee function because it doesn't tell us much. And then let's take a look at this part. So it's going to calculate the amounts of both tokens given the liquidity that it's being burnt. The liquidity is represented by the pool tokens that were sent to this contract. And it's going to calculate the proportion over total supply, get the amounts, and then going to burn the liquidity and transfer both of these tokens to the user. Afterwards, it's going to calculate again the balance and update the tracked reserves of the contract. Okay, now that we have our core concepts of Uniswap already learned, then we can move into coding one of these pair contracts in Cairo. We're gonna be replicating the same concepts that we saw just now in the main contract from which is written in Solidity. And also I want to use this one of my tools, one of my favorite tools, to showcase interactions with contracts on StarkNet. So I'm gonna be cloning this first, and I'm gonna put it a name. I'm gonna call it Cairo pair v2, and I'm gonna do course the modules. All right. Then I'm gonna feed into this repository here. Cairo pair v2. I'm gonna open my code editor. I'm gonna place it such that we can see clearly. Increase a bit the size. Gonna open the terminal here as well. I'm gonna yarn chain. I'm gonna yarn install. Then yarn chain. So while this is loading, I'm gonna explain what are we gonna be doing. So we're gonna be writing this contract in Cairo, not as a whole. We will be skipping a few things such as the mint fee, for example. And let me refresh this. We will be also skipping things like the cumulative blast because this is used here on mainly this side. Okay, so we're gonna be doing a minimal version of this Uniswap v2 pair in Cairo. All right, let's go into it. So this is loading. This is the localhost DevNet that I'm trying to run myself. I'm gonna go into this contracts repository, contracts folder. I'm gonna add my contract called pair.cairo. Right. Now let's just start by creating our main contract interface. All right, let's declare a contract. It's gonna be called Cairo pair. Just pair contract. This will require us to do some storage. And yes, struct for storage. So let's take a look at the Solidity version. What things we need to have. We need factory. We are not using a factory because we're not doing that. But we have a token 0, token 1. This is very important. The reserve 0 and reserve 1 is the tracked balance of the pool. So it doesn't represent the balance of, but it represents what it's being tracked so far. We're not gonna be using these three as these represent are used on some functions that we don't mind for now, and some getters like get reserves and safe transfer. Okay, now this v2 pair is also an ERC20, so we're gonna be writing some simple ERC20 related functions on top. So we are building a very minimal version of this pair. Okay, so let's first start with the storage. Size a bit. All right, let's start with the token 0. So token 0 is going to be a contract address. Then token 1 is also going to be a contract address. We also have the reserves as we saw before. Reserve 0, it's going to be U256, and then we have reserves 1, which is also U256. Some ERC20 helpers. We are not implementing the whole ERC20 component here. We're just going to be using a couple of helper functions so we can showcase how this works. So balance of using this. Right, this works. Now, one more important thing we're missing is the K. So the K is going to be helping us maintain the constant product formula. Now, let's start with the main function of these pairs. So let's do the mint function first. Okay, the mint function, what it does, it's going to get the tokens that were sent, and it's going to mint the proportion of the tokens, but with a subtle check at the very beginning when the minimum liquidity is locked to the address 0. Basically, this minimum liquidity is burned. Okay, we're gonna be doing this logic here. We're gonna define our StarkNet interface, so we know we're keeping track of which functions we are integrating. I'm gonna call this iPair and control state. right. Let's take a look first to see if this thing compiles. Okay, this is correct. No, no, this is not yet correct. We have to add our contract here. Now this is giving me an error here, so we are missing this import. And we have to use it as well here. Now this is going to be a legacy map. All right, now this should compile. All right, cool. Now let's actually write first a helper function here. Helper view functions. So one of the main view function, the one that every pair has, is the reserves function. So it's gonna give us two numbers that represent these two here, which are the tracked. These are the tracked balances of both tokens on the pool. Now I'm gonna implement this through I'm gonna put this on my API of the contract. I'm gonna do this API embed v0, and I'm gonna do this implementation of pair implementation of iPair of my contract. And I'm gonna start with my function. I'm gonna start with the view functions here. I'm gonna keep the view functions at the bottom, get reserved. So this is already here, iPair. I need to import my iPair, so I'm gonna put it here. Okay, pair implementation. Okay, we're missing the mean, so I'm gonna just first comment this out. We're not using the mean yet. I'm going to, let's just read. We're gonna be reading from here and reading from here. Let's see if this compiles. Okay, so this compiles. It's working well. Now, in order to visualize this, I'm gonna deploy this here, so we can just keep track of what's happening there. How this contract is gonna be changing along the way. Oh, before we actually deploy this, we need to write some very simple deployment scripts. We're gonna be needing a mock token contract in order to create this. So I'm gonna be using one sample mock token that I have. It's gonna represent a dummy ERC20, maybe whatever. So this is a sample ERC20 that I have. And then I'm gonna write my deploy script as well. So I'm gonna be creating some of these tokens. So I am going to create these two. I'm gonna do USDT and I'm gonna do ETH. Right, initial supply and the names of them. ETH. Okay, and then I am also going to deploy my contract, the one that I'm writing just now. So I'm gonna just directly deploy that contract. I'm gonna give it, so we don't have a constructor yet. I think we need to work on that first. Let's go for a constructor. So we define our constructor with this tag here, and we do constructor in StarkNet, and we do ref of contract state, and we're gonna pass basically the most important components of this contract, which are the tokens 1 and token 0, token 1. Then we will just write them to their corresponding storage slots. Let's just check if this compiles. Seems like it's all good. We can keep going. Now let's take a look at the deployment. So we're going to be passing the token 0 address, and this is going to be USDT. We're going to pass the token 1, and then we're going to pass the contract name, which is going to be the pair contract. And I'm going to call it workshop USDT ETH. Now let's see if this actually can deploy. Deploy. We need to also import our mock tokens here. All right. So we created two tokens, mock tokens. We put them as constructor arguments on our pair contract, and we're getting the reserves of them. So if we test this now, we're gonna go here. I can take a look here how this is looking on localhost. I'm still not seeing them yet. It's still loading. So I can see two mock tokens being deployed and then my pair contract. Right, this should be appearing here very soon. Right, I have my workshop token. I can get the reserves. Oh, it's actually a write function. Let me change these to a read function instead. And let's also add something that tells us the token 0 and token 1. Right. Now, let's see if this can compile. Okay. While this is applying, let's move into doing the mint function, the first function. So I'm gonna start this function here, mint. I'm gonna reference my contract state, and I'm gonna write the to address, which is going to be the contract or the user that is going to receive those tokens, liquidity tokens, and I'm gonna output the amount of liquidity tokens that were minted on this function. Now, if we check the Solidity version, we have a helper function, which is this one, right, the reserves. So we need to first declare our reserves, right? So I'm gonna declare some local variables for the reserves of 0 and the reserves of 1. I'm gonna get them through the function that I already defined as get reserves. So I already have these in my function here, in my function mint. The next thing that we have to do is we need to read the balances, and for that we will need to import on our contract here in the dependencies, we need to import the dispatcher for ERC20. So let's do that. Disabling token interface, then ERC20 camel hatcher and the ERC20 camel dispatcher trait. Let's see if this is available here. I think yes. Okay. Let's see if this compiles. Okay, yeah, it's good. We're just missing this return on the mint, but it's all okay. All right. Now we need to use these. We need to get the balances, right, of these two tokens in the contract. So we call it balance 0. It's gonna be the dispatcher with contract address. It's going to be the self token 0, and we're gonna get the balance of the token, the balance of this contract. So I'm gonna use get call contract address. This is an internal, there's a helper from a StarkNet. So I'm gonna use a StarkNet. Alright, I'm gonna maybe use more other functions later, so I'm gonna put this there, and this should work fine. Now let's do the same for the second token. Done. The next thing we have to do is we need to calculate the amounts that just came into the pool, right? So it's just a subtraction here from both. We have this done, and now let's calculate the tracked total supply, right? Supply, it's basically gonna be a total supply that we have here. I'm gonna modify these names. Okay, we've got a draft total supply. The next thing we will do is we need to consider the edge case that we mentioned before, the if and else of when the total supply is 0. So we need to burn the minimum liquidity. So this is a constant number that is equal to 10 to the 3 way. Okay, so let's go to the mint and let's write it down. So it's right here, it's constant minimum liquidity. That's gonna be, yes, 1000. Next thing we have to do is we need to say if the total supply of these is equal to 0, then we will be doing something, burn 1000, and then if not, we do the other operations. The operations are easier, so let's take the left hand side first. When I say the left hand side, referring to this part here, so we can do the minimum from both, and then this one here. I'm actually going to create a minimum minimum function, helper function here as an internal for the sake of this simple tutorial. So I'm gonna do this internal generate rotation of internal trait, and I'm gonna do this function. So given two numbers, I am going to calculate the minimum of both. That's it. So if a is less than b, I return a, and or otherwise b. That's it. The left hand, which is the other side of this, it's going to be equal to the square here. No, it's going to be the multiplication of the amount and total supply. Basically, it's going to calculate the proportion of this amount against the total supply with the reserves. So we will be doing this outside left hand, so we can use it on the minimum function. It's going to be 0 times total supply over reserves of 0, and the same for the other one, for the amount 1, the token 1, and then the liquidity is going to be this. Okay, now we didn't define our liquidity yet, so our liquidity is going to be defined outside the if, and I am going to name this, like, to put as a value 0 and make it mute. Okay, great. Now in order for these to stop giving me errors, I'm going to just return the liquidity, so like the return value of the function. Next thing we can do is we will consider the edge case of the total supply equals 0, and we're gonna be using this helper function called u256 square root that you can get from the core StarNet integer library. This will help us calculate the square root of the multiplication of amount 0 and 1. So like the square root. Let's declare this, because a u256 square root is going to give me a u128. I'm gonna cast this to 256 again so that we can use it with the other ones. And the liquidity is going to be equal to the subtraction of these two, because we're going to be burning now this minimum liquidity, right? So need to be doing this to the address 0. All right, now we need a function that represents the mint. This is going to be the internal mint of the ERC20 that represents the shares of this pool. Yes. So this is the legacy map we're using. So read. Alright, we update the balance of the user and we update the total supply. Let's do the address 0 for this as well. Alright, after we have minted the 0 address, which is basically burning those tokens, we are going to check whether the liquidity, the resultant liquidity, is greater than 0, and then otherwise revert. And finally, we just mean tokens to the user, and we also have to update, but we don't have an update function yet. We're gonna be doing this now. We will update with these two tokens right over here. Actually, the two balances here, balance 0 and balance 1. What this is going to be doing is just updating the tracked reserves that we have. So as you see here is updating the reserves of 0 and 1 using the balances that we pass, and we do this just to keep track of the k, the constant. So our main function is done, and let's see if this compiles. All right, this is good. Now, what is the next function we should be taking a look at? It's going to be the burn and then the swap. So let's do burn first. The burn will give me two outputs. One of them is going to be the token 0 amount. The other is going to be the token 1 amount. Why? Because as it meant we have to deposit 2 tokens and burn and get some liquidity. Just 1 liquidity token and deposit 2. Here we will be sending liquidity tokens and burning those and getting in exchange some of the tokens like token 0, token 1. So that's why we have 2 outputs here. Now let's implement the function. So this is going to be the same. And it's going to also give me 2 numbers. Okay. There we go. This is the function. Now, the first part is basically the same as the need. We have to keep track of these reserves, right? So we need to get them from our helper function reserves, get reserves. Next thing we will be doing is we need to track as well the tokens that we have in this pool, and we're gonna be doing these by getting the tokens, get token 0 and get token 1, or we can just do token 0 read and then token 1 read. The next thing we will be doing is calculating the balances, both tokens. Finally, I'm going to check how many of these liquidity tokens were sent. Here. How many of these were sent to the user? This transfer from is not yet done, so we need to add it here. We will skip this part first. So the transfer from is going to be one of the ERC20 functions that we can call on this pull token. Now we're also gonna be calculating the total supply that we have now, which is going to be this. And then we're going to calculate the proportions of both tokens compared to the liquidity that is being burned and the total supply. And finally, we have to assert that these 2 amounts are greater than 0, otherwise we're not burning enough liquidity. Finally, we do our internal function burn, which we don't have yet. And at the end, we transfer the tokens to the caller, to the tool. And then let's see this. So we transfer the first amount, the second amount, and then we update the balances. We return both amounts as the return outputs of this function burn, and that's pretty much it. We need to create a few functions that represent the ERC20, like transfer to, and balance off. Right, we're gonna do this. It's a minimal version of a ERC20. All right, so the supply keeps the same, current balance keeps the same. Oh, supply doesn't change. Need to get the caller address. Okay, this should be working. Let's start compile. Okay, we need to define our function burn. It's going to be very similar to what mint does. So it reaches the supply, the balance, and then updates by subtracting both of them. That's it. Okay, so now we have a burn function, and we are missing the one and only swap function. Let's write it down here. Right, let's just start with some asserts first. Let's do assert that both amounts are greater than 0, or at least one of them is greater than 0. The next assert will be according to the reserves, so let's get the reserves first. And let's make sure that the amounts out are actually greater or actually less than the reserves, otherwise we don't have enough funds, liquidity for this trade. Let's make sure this compiles. Okay, next thing we have to do again is read the tokens. Token 0 and the token 1. And then we have to compare that these two address is not one of these tokens. Now if the amount of 0 out, we transfer them. If amount of 1 out is greater than 0, we transfer them. And also if call data length is greater than 0, we do a flash loan or a flash swap. So I'm gonna call this self flash swap 2. I'm gonna put data here. I'm gonna comment this out first, and I'm gonna declare my flash swap function here. So yes, I'm gonna be using another darknet call, which is going to be the call contract syscall. Right, and I'm gonna be doing this here. So what I do is I need to call contract syscall to data. I'm gonna pass an entry point, which is going to be the uniswap or pair flash swap callback. It's an entry point of this that has to be defined on this contract to receive this data, and we can define it here as a constant. So I'm gonna put some random number as an entry point for now. Keep it as a to-do to change this to the real function name. Yeah. So this should work. We're gonna declare this as failed. Let's change the import trace for this call contract syscall. Okay. Okay, after this section is done, we need to read the balances. The new balances means that after the flash loan has been done, you have to basically send the tokens back or repay the loan that you just did. And this is what's going to be being trapped just now. So we read both balances for both tokens on this address on this contract, and then we are going to calculate the amount in. Zero in, it's going to be a 256. I'm gonna set this to 0, and I'm gonna put another for amount in 1, and I'm gonna say that if balance of 0 balance of 0, it's greater than reserves of 0 minus the amount of 0 out. I'm gonna place this to the amount 1, and I'm gonna do the same for the amount 0, amount 1, both of them. Then I'm going to make sure that the inputs are correct. At least one of them has to be greater than 0, otherwise there's no enough input amount for this function call, for this swap, for this trade. The next thing, I'm going to calculate the balance 0 adjusted, which is going to represent the fee. I'm going to declare this fee here, basis points. So fee basis. Fee, I'm going to do this in 30, going to represent of 10,000 basis points. And then I'll do this 10,000 here and fee. Do the same for the second one, and I'll try to compile to see that everything's going well. Constant fee. Okay, this is good, this is working. Finally, let's assert the K. So this is what it's all about. Keeping track of the K and making sure this is at least constant if there is no fee. We do this through checking the balance adjusted, which is the balance with the fee, times the balance 1 adjusted. It has to be greater than or equal to the tracked reserves 0 times reserves 1. And we use this to account for this calculation here. Otherwise, the error will throw us a K error. Finally, we just do our update of balances based on this, and this should be working. Okay, now let's see if we can deploy this contract. Let's actually add some helper function for price, so we can see how this price fluctuates. So I'm gonna call this get amount 1 out. I'm gonna pass an amount 0 and amount 0 out as well. Okay, I'm gonna put this here for the ERC20 functions. So this should calculate the amount with fee. I'm gonna do here as an if instead. If just return 0, otherwise amount 1 with fee. Let's use the same function for the get amount 1 out, and let's deploy these two contracts. All right, now let's take a look here. First of all, I'm gonna connect my wallet here. I'm gonna mint myself a few USDT. So I'm gonna do, let's say 1,000, and then I'm gonna also transfer this pair address. I'm gonna copy this pair address and I'm put it in here, and then I'm gonna pass one ETH. So I'm gonna pass 999 again. I need to pass the 1,000. I'm passing 1,000 USDT to the pair, and now I'm going to pass 1 ETH to the pair. So I need to get myself some ETH first. I'm gonna get just 1 ETH. This is 1 ETH. Then I'm going to send this ETH to the contract, pair contract. Okay, so now this contract has 1,000 USDT and has 1 ETH, which means that after we call the mint function, we should have some liquidity tokens that represent these proportions, 1,000 and 1 ETH. Let's see, right? Now we see that the reserves have changed. Now we have these reserves And let's try to see what is the amount out for one for ETH. If I pass, let's say 100 USDT, how much ETH do I get? Okay, so I will get this amount of ETH if I pass this amount of USDT. Now, if I pass, let's say this amount of ETH, I'm gonna get a certain amount of USDT, right? This has to be 100. There's not enough amount of USDT to account for this amount of ETH that I'm sending, and that's why I'm not getting anything here. Okay, so now this is the you can think of this as the price of sending this amount. I'm gonna do this 100 USDT. It's gonna give me this amount of ETH. Okay, let's recall this amount here. Okay, now we will change our wallet, and I'm going to do a swap. So I'm going to give myself some USDT. I'm gonna do 200. And then I'm also going to transfer them these 200 to the pair contract to do my swap. I come to the pair contract, and if I input here 200, I am expecting to receive this amount of ETH. This amount of ETH. I'm expecting to receive this. Okay. Now let's get this amount. Let's put it here as is the first token amount. Get one amount, 0 here. And I'm gonna put my address. I'm gonna be the one receiving these tokens. Here I'm gonna leave it as empty, and I'm gonna send this transaction. Now let's see if this works. Okay, this works. Now let's see how this is going to change. So after I've done this trade, the amount out, which is like representing the price, is like a ratio there. We should change. So we should see that this is different, and let's see how different it is. Now you see that for the same amount of USDT, I will be getting less ETH. And the reason is because I sent USDT and I got some ETH because I am buying ETH using USDT. So the amount of ETH is less. For this reason, the amount of the ETH is more pricey. And for the same amount, I'm getting less. If we keep repeating the process, this amount will be just decreasing and decreasing. And this is how it works. So again, you send tokens to the pair, and then you do a swap or you do a mint. Everything that we did just now by sending tokens and calling the swap and calling the mint, this thing is done through the routers of Uniswap.